We look at some practice questions on work, power, and energy. We've been given a first question where we've got an electric motor with a 15 kilowatt output which provides power to an elevator of a building. The total mass of the loaded elevator is 1 ton. What is the minimum time taken for everything, the elevator and every mass in it, to rise for a 30 meters height from the bottom to the top? So we know that power is given by work divided by time. Now, because there is a rising here, work is given by mgh, and so power becomes work is mgh and then divided by time. And the power has been given in kilowatts. So 15 kilowatts, converting it to watts, we're going to multiply by 1,000. That is because a kilowatt we multiply by, we're going to put a kilowatt down and then a watt on top. And you know that in 1 kilowatt we have got 10 to the power 3, which is 1,000. Like, just kilo means 1,000. So this and that is going to cancel out. So this is the power which we have now. And we know that power should be equal to work. I mean mgh, work over time. The mass now is 1 ton. Now also the 1 ton we need to convert it to kgs. In 1 ton there is 1,000 kgs. So that and that is also going to cancel. And then multiplied by g, which is 9.8 meters per second squared, and then multiplied by the height, which is 30 meters. And then everything here we are going to divide by, dividing by the time, t. So 15 multiplied by 10 to the power 3 is going to give us 15,000. And then going to the other side, 10 to the power 3 multiplied by that, multiplied by that. So 1,000 multiplied by 9.8 multiplied by 30 gives us 294,000 divided by t. So to remain with t, we are going to cross multiply. So that will be 15,000 t is equal to 294,000. So just divide by 15,000, because it will be here t times this. The 15,000 is going to be on this part. So we are going to divide both sides by the 15,000. That's why I've just written it on the other side. So this is going to give us 19.6 seconds. So that is the time that is going to take. The next question: what force is required to stop a 15-gram bullet that is moving at a speed of 400 meters per second in a distance of 20 centimeters? Now, the first thing is, let's convert this which we have. We've been given the mass of a bullet as 15 grams, which we can convert to kgs. We know that in one, okay, let's say, so the easiest way to convert is, we want to go to kg, so we write a kg on top and then a gram down, so that a gram and the gram is going to cancel. But you know that in 1 kg you have got 1,000 grams, 10 to the power 3. So that is going to give us 0.015 kgs. And then we've been given the displacement, which is 20 centimeters. Also convert that to meters. We know that in one, okay, let's have a centimeter face down before we even do that. A centimeter down, because we have got a centimeter on top, and then a meter on top. In 1 meter we know that we have got 100 centimeters, so that is going to give us 0.2 meters, because the centimeter and the centimeter is going to cancel out. And then we begin given the final velocity as 400 meters per second. Now this is the velocity at which the bullet is moving, so it is u. Now we want to stop this bullet. What force is required to stop? So we want the final velocity to be 0. What we need to get to understand is work is equal to change in kinetic energy. Okay, this is referred to as the work energy theory. Work is equal to change in kinetic energy. Now, change in kinetic work is given by force times displacement. Okay, and then cos theta, and that should be equal to the change in kinetic energy is given by half mv squared. This should be the final kinetic energy minus the initial kinetic energy. Now we want a force that is going to stop something that is moving. That means that force should be acting in the opposite direction. If this thing is moving forward, that force should act in the back direction. So that would be the force. And then this thing is moving like that. So notice that the angle they are going to make is 180 degrees. So the force, which we don't know, is just F, The displacement, we know that is going to cover its distance of 0.2, and then cos, the angle is going to be 180. Now the final kinetic energy is going to be 0 because we want this thing to stop. When something stops, the final velocity is 0, as you can see here, and when 0 multiplies anything, it is still going to be 0, and then minus half. The mass, of course, is 0.015, and then the final if the initial velocity, I mean, yeah, this is the initial velocity, is 400 squared. Cos 180 is a negative 1, and negative 1 by 0.2 times f, it will be negative 0.2 f, and that should be equal to, if we punch on our calculator, negative 0.5, which is the half there, multiplied by 0.015 multiplied by 400 squared, supposed to get negative 1200. To remain with f, we're going to divide by negative 0.2 on both sides. So that is going to give us 6,000 joules, which you can also say 6 kilojoules. So this is the force that is needed to stop this bullet. Alright. Next question, we've been given a 200 kg car traveling at 20 meters per second comes to rest on a level ground in a distance of 100 meters. How large is the friction force on the car? So same here, this car is being stopped, and so friction always acts in the opposite direction to the direction of motion. So if you've been given a car, alright, so say this car is moving forward at this velocity called 20 meters per second. The only way that this car is going to stop to have a final velocity of 0, because it's moving at this velocity, and we are going to call it as the initial velocity. A friction always acts in the opposite direction, and so we are going to use also the work energy theorem. Work is given by change in kinetic energy, and work is given by Fs cos theta, where F is applied the force we are talking about, and then S is the displacement, and then cos theta, and that will be equal to the change in kinetic energy is half m change in velocity squared. So this is change in velocity, that is what we call change. Like kinetic energy is given by half mv squared. So when we put change here, we are supposed to put change there also. So the change is given by final kinetic energy minus initial kinetic energy. Now the friction we don't know, the distance we know it should come to rest in 100 meters, and then cosine, because this is friction, see the direction of motion is forward, but friction is acting in the opposite direction. So the angle is always 180 in that case, and that should be equal to half. The mass is 2000. Change in velocity, it is final velocity. Whenever we talk of change, it is final minus initial, but the final, it wants to come to rest, the final is going to be 0. The initial, it is moving at what? 20. So we are squaring this to remember it is change in velocity square. Please, this you should not be able to square. Don't put the square outside, because we can see a square on top there, so we put a square outside. We don't do that. Alright, we square individual terms inside alone. And so that is going to give us cos 180 is a negative 1 multiplied by this 100 by f, that will be negative 100f, is equal to, this will give us 2 into 200, that will be 100, and then 0 minus 20 squared, that will be negative 400. Okay, so the friction therefore is going to be equal to this 100 and this 100 is going to cancel, and then this negative and that negative, they are also going to cancel. That will be 400 joules. So that will be the friction, then that is going to stop this vehicle from moving. Alright, so we've been given another question. Compare the potential and kinetic energy of a 1200 kg car on top of a hill. So assuming you got an hill there, and then this hill is 30 meters high. You've been given a car on top there. Okay, in that manner. And then its mass has also been given. Now, when moving at 100 kilometers per hour down, so when it is moving at this speed down, which is more damaging, crashing into a stationary object at the speed, at this speed, or dropping from a height? What would be more damaging? So when this car is moving and then it hits something that is stationary here, or it drops from the top down, which one is going to be more damaging? Alright, so what we are going to do is we first want to compare the kinetic energy and the potential energy. So the kinetic energy is given by half mv squared. So that will be given by half. The mass is 1200. We've been given the velocity as 100 kilometers per hour. So we first need to convert that kilometers per hour into meters per second. So we're going to say 100 kilometers per hour. Let's convert first the kilometers. The kilometers is on top, so we're going to bring it down. And then we're going to have a meter on top. You know that in 1 kilometer we've got 1,000 meters. And then we multiply. We have got a hour down, so we're going to put a hour on top. And then we want to in seconds. You know that in 1 hour we have got 3,600 seconds. So what will be the value then? Notice that this hour and the hour is going to cancel. Kilometer and the kilometer is going to cancel. Alright. So that is going to be 100 multiplied by 1,000 and then divided by 3,600, which is 27.78 meters per second. So that is the one we are going to use here. 27.78 squared. So that is going to give us that value squared times 1200 then divided by 2, which is 462,962.963, which I can also write in standard form. So I'm going to move this decimal point 1, 2, 3, 4, 5. So that becomes 4.6 times 10 to the power 5 joules. Now let's calculate the potential energy. The potential energy is going to be equal to mass times gravity times height. The mass is 1200, gravity is 9.8, the height is 30. So that is 1200 multiplied by 9.8 multiplied by 30. So that is giving us 352,800. So the decimal point means it's there. So I can also move the decimal point to write in standard form 1, 2, 3, 4, 5. So that is going to be 3.5 times 10 to the power 5 joules. So this is showing us that the kinetic energy is greater than the potential energy. Now, which will be more harmful? Is it that when this car moves and strikes something that is stationary, or when it drops from the top to the down? Now notice that the potential energy is more than the kinetic energy. So this means that when this car moves and hits something that is stationary, it will be more damaging than when this car falls from that height to the down. Okay, so that is the meaning there. Alright. So I've been given a next question. A car is sliding downhill at constant speed of 8 meters per second. When it reaches an ice patch on which her skis moves with a negligible friction. If the ice patch is 10 meters high, as we can see, what is the car speed at the bottom? So at this point, the initial speed is she's moving at 8 meters per second. Now what will be the speed here? Now, according to the law of conservation of energy, the energy at the top should be equal to the energy at the bottom. Energy on the top there should be equal to the energy on the bottom. Now on the top, this person is going to have potential energy and kinetic energy. So potential energy and the kinetic energy at the top, let me call them 1 to represent top. And then they should be equal to the potential energy and the kinetic energy at the bottom. Let me call them 2 to represent bottom. Okay. Now on top, the we can simply first write the formulas. Potential energy is given by mgh, and then plus kinetic energy is given by half mv squared. But on the bottom, this person is moving, so even at this point, the person hasn't stopped moving, and so the potential energy is 0. If you want to consider, the potential energy is given by half potential energy is given by mgh. So at this point, this is the point which we are using to find this height. So that means at the bottom the height is 0. So when the height is 0, that means mgh is going to be 0. That's why the potential energy is 0. And the kinetic energy is half mv squared. So notice that the masses are going to cancel out. That's why they've not even given us the mass of the person. So that would simply be gh is equal to half, gh plus first half. Now this, which I've written as v, is supposed to be u because that's the initial, and that would be equal to half v squared. So g is 9.8, the height is 10, and then plus half. The initial speed is also 8 squared, and that should be equal to half the final, which we don't know. So that is going to give us, let me start writing first this. So that will be half v squared is equal to, if we multiply this, that will give us 98, and then we add this, that is going to give us 130. Okay, so if we cross multiply, that will give us v squared is equal to 2 times 130. To remain with v, we'll take the square root on both sides. So the velocity at the bottom then is going to be 16 meters per second. Alright. Given another question, a 25 kg box is put up a ramp which is 20 meters long and 3 meters high by a constant force of 120 newtons. If the box starts from rest and has a speed of 2 meters per second at the top, what is the friction force between the ramp and the box? So we've been given a ramps like that. They've told us the height of the ramp is 3 meters, and then its distance is 20 meters. And then you've been given a box that you are pulling up by a certain force, a 120 newtons force. And then we know the mass, of course. Now, this ramp is rough. It has got friction. Friction, we know that acts in the opposite direction. And that is obviously kinetic friction because something is moving. Now, the question is, what is the friction force between the box and the ramp? Okay, so what will be the friction force in this case? So we are going to use conservation of energy. So energy at the start should be equal to energy at the end. So not really energy at the start and at the end, but let's say work. So the work done, okay, so first have the work which is done, it should be equal to the work done by friction plus the work done by, really not work, but plus the kinetic energy plus the change in potential energy. So this is the work that we are doing by applying this force which is here. So this work, some of it will make this thing to start moving up. It's going to overcome the friction. It will make this thing to start moving. And then remember, at this point it was coming from rest. It had potential energy. It's going to overcome also potential energy. Okay. So this is work done by the force which we applied. And we know that work done by the force is given by force times the displacement. Remember, the displacement is going forward. It's in the same direction. Let's say Fs cos theta. Let me just write the formula in full. Work done by friction also be friction times displacement cos theta, and then plus kinetic energy is given by half mv squared, and then potential energy is given by half, not by half again, by mgh, sorry. So the force applied is 120, the distance is 20, the distance of the incline, and then the angle, because the force is going the same direction as the displacement, the angle is 0. So 0 degree, and that should be equal to the friction, which we don't know. Okay, and then the displacement is the same, 20, but the angle, notice that this mass is going up, friction is going down, so the angle is going to be 180, and then plus half. The mass of this object is 25, the velocity at which it is moving at the bottom just is 2 squared. Okay, and then plus the mass again is 25, g is 9.8, the height of the ramp is 3. Okay, so that is what we have. Now if we cos 0 of course is 120 by 20 is going to give us 2400, and that is going to be equal to 20 times 180 is giving 3600 f, and then plus we get this portion 1/2 multiplied by 25 multiplied by 2 squared, which is giving me a 50, and then 25 by 9.8 by 3, that is giving me 735. So if I take these two over the other side, they're going to become negative, so that will be 2400 minus 50 minus 735 is equal to 3600 f. So 2400 subtract 735, also subtract 50, that is giving 1615, and that should be equal to 3600 f. Okay, so now we want to remain, sorry, what I did here, I missed out something. This I left out a cos, which is very important at this point. This is not 180, that's why I'm going on with a wrong value. So this value here is not going to be true. Same with this one, which is here, it's not also going to be true, even there. Alright, that is a very big mistake I would have made. So there is cos here. So what we are saying is cos 180, and you know that cos 180 is a negative, okay, is a negative 1, and then that negative 1 multiplied by the friction, let me just pray, so 20 cos 180 is the negative 20, so that is negative 20f. So that is the one which is going to even remain in negative 20f, even there to be negative 20f. So therefore the friction is going to be equal to 1615 divided by negative 20, which is giving negative 80.75 newtons. Really the negative sign is just telling us it's in the opposite direction. Okay, yeah, it's just in the opposite direction. We know that. So work done by friction is negative. Work done by friction is negative because it reduces the motion that you're talking about, or it reduces the actual work. Alright, another question given. A 6.5 box starts to slide up a 30-degree incline with an initial speed of 2.2 meters per second. It stops after sliding 40 centimeters and slides back down, assuming a constant friction force is impeding its motion. How large is the friction force? Again, we have been given so we have again that the incline is 30 degree. We've got a mass which is, they say, sliding up, so that is the direction of motion, is sliding up, and then we know that the velocity at which it is moving is 2.2 meters per second. Now notice that there is no any applied force here, but it is sliding up. Alright, and they've told us there's a constant friction opposing the motion on this object. And then it moves for 40 centimeters. So it moves, let's say, from this point where it is, and then it covers 40 centimeters to reach somewhere. And then when it reaches where it reaches, let's say it reaches here, and then it starts going back again. So let's first collect the data that we have. We've been given the mass as 625 grams. Let's convert this mass into kgs. We have got a gram down, so we are going to have a kg on top. In 1 kg, we have got 1,000 grams. So that is going to give us 0.625 kg. And then you've got a distance, which is a displacement of 40 centimeters. We have got a centimeter on top, we put it down, so we have a meter on top. In 1 meter, we've got 100 centimeters. That will give us 0.4 meters. The other thing that we have is the initial speed. Okay, the speed at the start has been given as 2.2 meters per second. So again, how do you find the friction force that is going to be impeding the motion of this object? Now in this case, the first one there, notice that we don't have any applied force. We don't know the applied force. So at the start, it says a 625 box starts to slide. So it just starts to slide and it is moving at that value. So at the start there, it has got kinetic energy. And then as it is going, energy is always conserved. The energy initial should always equal to the energy final. At the start, it only has the initial kinetic, it only has kinetic energy. So all this kinetic energy is going to be converted into potential energy when it reaches to the top. But same, this kinetic energy, some of it will be used to overcome the friction, and that will be work done by friction. So the friction is also doing some work against the motion. So that becomes the formula. The work at the start is equal to the work at the end there. Now the kinetic energy is given by half mv squared. Potential energy is mgh, and that, okay, and then plus work done by friction. Work done by friction is simply friction times the distance. At this point, I don't want to put cos theta. I'll talk of that later then. So that we are saying force times the distance. So that is half. The mass we found as 0.625. The velocity which is moving is 2.2 squared. And then that will be equal to, the mass is still 0.625. Gravity is 9.8. Now, how do you find the height? Okay. We don't know the height, but we know the distance is going to cover, and then we know the angle. So let's say this is the height, let's call it h. So we've got a triangle like this, where you know the h, and then you know this as 0.4, and then you know the angle theta. So this is the opposite, this is the hypotenuse. So since the angle 30 is equal to the opposite, which is height, over the hypotenuse, which is 0.4, that means the height is going to be 0.4 sine 30. Okay, and you know that sine 30 is simply half. So 0.4 times half is 0.2. And then plus F, the friction, which we don't know, but you know the displacement is still 0.4. So we go on multiplying half, just the first portion, times 0.625, and then times 2.2 squared. That is going to give us 1.5125, and that will be equal to 0.625 multiplied by 9.8 multiplied by 0.2. That is 1.225, and then plus 0.4f. So I can take this the other side, so that will be 1.5125 subtract 1.225. So that is going to give us 0.2875 is equal to 0.4f. So to remain with f, that will be 0.2875 divided by 0.4, which is going to give us 0.71875, which I can simply write as 0.719. Okay, so this is a force, and force is measured in newtons. So that is the force then for that one. So that is a friction that is going to be reducing the motion. So I've just written it positive like that. Otherwise, friction acts in the opposite direction. That's why you can see if we use cos theta, it would have been cos 180, which it would have given us the same value but negative. The negative would have just told us the direction in which it is moving. Alright. Now the second question we've been asked. What is the block's final speed as it reaches the bottom? Remember, it has gone, it has reached the top, and then at the top it starts sliding again, going down. Now what will be the final speed when it reaches the down? So for the second one, notice that it is on top. On the top, if it reaches on top here, what is going to have is potential energy. When it starts sliding down, the potential energy will now start to be converted into kinetic energy, and also the friction is also going to be doing some work. That is what happens. So as it was going down, we first had kinetic energy, which was converted to potential and work done by friction. We know that potential energy is given by mgh, and that is equal to half mv squared plus work done by friction, which we can just say fs. Okay. So the mass is 0.625, g is 9.8. The height, again, we already derived the height. We said height is 0.4 sin 30, which is 0.2. And that should be equal to half. The mass is 0.625 v squared. Work done by friction. We already calculated the friction as 0.719, and then the s, which is the displacement, is still 0.4 because it wants to cover the same distance coming from the up to the down. That is still 0.4. So what is this going to give us? On the first one, 0.625 multiplied by 9.8 multiplied by 0.2, that is giving 1.225, and that will be equal to, if we take this portion, 0.625 divided by 2, that is 0.3125 v squared, and then plus 0.719 multiplied by 0.4, it is 0.2875, 76. So I can take this one the other side so that it becomes negative. And so what we are going to have is 1.225 subtract 0.2876, and that is going to give 0.9374. That will be equal to 0.3125 v squared. So to remain with v squared, we are going to divide 0.9374 by 0.3125. That is going to give 2.99968. So to remain with v, we take the square root. That would be 1.73 meters per second. That is then the velocity. Alright, we've been given the next question. A toy car starts from rest at the top of a 12 meters crest and climbs to the next crest, which is 9 meters high. How fast will it be moving if it passes point B if the path is frictionless? Now, this is point A. This is point B. And we know that the energy on one point should be equal to the energy on the other point. And the energy at this point is the sum of potential and kinetic. Same here, the energy at this point is the sum of potential and kinetic. So what we are saying is potential energy at A plus plus kinetic energy at the same A should be equal to the potential energy at B plus the kinetic energy at also B. The potential energy at A, that is given by mgh, and then plus kinetic energy is given by half m v squared. Then potential energy at B is given by mgh also, plus the kinetic energy at B is half mv squared. Notice that the masses are going to cancel out because it's all the same, it's the same mass. So remain with gh plus half v squared is equal to gh plus half v squared. This v is at B, and then this v is at A. So we go on, our g is 9.8, our height at A is 12, then plus half the velocity at A. It says it starts from rest, so there's no velocity, it's 0, and that should be equal to g at B is 9.8, and then the height at B is 9, then plus half the velocity squared, which we don't know. So 9.8 multiplied by 12, this portion is giving us 117.6, and that will be equal to 9.8 multiplied by 9, which is 88.2 plus half v squared. So I take this one, the other side becomes negative and subtracts from 117.6. So we're saying 117.6 remove 88.2. That gives 29.4 being equal to half v squared. Then we can cross multiply. We multiply a 2 by that one. So that gives us v squared to be equal to 9.4 times 2, which is 58.8. So to remain with v, we are going to square root on both sides. So that will give us 7.7 meters per second. Okay. Another question given. A crate is on a ramp which is frictionless. How long would it take to slide through a distance of 1 meter? And we know that the ramp is 40 degrees. So how long is it going to take to slide through that distance? So we're asking for the time it's going to take to slide for that distance. First thing that we want to find on is the net force acting on this object is mass times acceleration. The only force that is making it to slide from that point going down is Fg. Okay, like it's the force due to gravity, or the x component, I mean, of the weight, because this thing has got a weight, and weight always points downwards. Let me just write that much better. Weight always points downwards in that manner. And then we've got a normal force on the surface of this object as n. So if we extend this normal force, we are going to have a line which is like this. So if we join now this to make a simple triangle like that, this component which we can see here will be the component of the weight, which will make now this block to slide down, and that's what we call Fg. It's the component, x component of the weight. Okay, so we are saying net force is caused by the x component of the weight, which is simply Fg, and that should be equal to mass times acceleration. But how do we find Fg? Notice that this angle which is here is the same as the angle of the incline, and this side is opposite to that angle, so we're going to use sine. So it will be weight, which is the hypotenuse, and we know that weight is mg, and then sine the angle which we have of the incline theta. That will be equal to mass times acceleration. So the masses are going to cancel out, so we're going to remain with acceleration being equal to g sin theta. So our g is 9.8, and then sin the angle is 40, so that is going to give us 6.3 meters per second squared. That's the acceleration. Now the question is, how long? We want the time. So the only way you can find the time, let's go to the equations of motion. We've got v squared is equal to u squared plus 2as. We have got v is equal to u plus at. We have got s is equal to ut plus half at squared. Notice that if we use this one, we have got the time. Okay, in that equation there is time there is distance, and also so there is initial speed. So we are able to use this equation because this one is sliding. That means at rest the initial speed is, I mean where it is coming from, the initial speed is 0. So we are going to say s is equal to ut plus half at squared. The s, it covers the distance of 1. The initial speed is 0. So times t, so this portion will be 0. And then plus half. The acceleration is 6.3. And then t squared. So that is going to give us 1 is equal to 6.3 divided by 2, which is the 3.16 t squared. Remember with t squared, we're going to divide 1 by that 3.15. This is actually 3.15, okay? That will give us 0.31. So we are going to square root to remain with t. And that gives 0.563 seconds. So that will be the time that is going to take. So again, another question. A 10 kg block slides on a 200 meters high hill with an initial speed of 12 meters per second. So what we have is something like that. Okay, so I've got this block which is at this point, and then it slides with an initial speed u of 12 meters per second. We know that this hill is 200 meters high. Now the question is the first one. What is the speed of the block when it reaches the bottom of the hill, assuming no friction? So using conservation of energy, the energy at the top should be equal to the energy at the bottom when it reaches here. So on top it has got kinetic energy plus potential energy. And then at the bottom is also going to have kinetic energy and also potential energy. So let's say this is, let me call this as A, this as B. So I'm going to say at A. And then this will be at B. Alright. So kinetic energy at the top is half mv squared. At the top again the potential energy is mgh. Kinetic energy on the bottom is going to be given by half mv squared. But the potential energy, notice that the height here is 0, or it is moving here, like it has not stayed. Maybe it might even exceed this place when sliding. Potential energy is going to be 0 because the height is 0. Okay, so notice that the masses actually going to cancel out. So we're going to remain with half u squared plus gh is equal to half v squared. So half u squared, the speed on the top is 12, and then plus g is 9.8. The height is 200. That should be equal to half v squared. So this portion which is here, if we press, okay, I left a squared. 12 squared is 144 divided by 2. Okay, so we have got 12 squared divided by 2, which has given me a 72 there, and then plus 9.8 multiplied by 200, which is 19. This is 1960. That should be equal to half v squared. So if I add 1960 plus 72, that's 2032, and that will be equal to half v squared. So to remain with the v squared, I'm going to cross multiply 2 times 2032. That will give 4064. So the velocity, therefore, we're going to take the square root of that value, which will give 63.7 meters per second as the first question. Okay, so that will be the velocity at the bottom then. Now, what if there is friction? So we've been told, what is the speed of the block at the bottom after traveling a distance of 500 meters given that the coefficient of sliding friction is 0.21. So in this case, at the top, this thing has got potential energy and also kinetic energy. At the bottom it will be moving, so it will have kinetic energy. But there is also friction, so it's going to also have some friction. So friction is going to do some work at the point B. Now the potential energy is given by mgh. This is at point A. Kinetic energy is half mv squared at point A, and that will be equal to the kinetic energy at B, half mv squared at B, and then the work done by friction. Let me just say work done by friction like that. So the mass in this case, our mass is 10, g is 9.8, the height is 200, and then plus kinetic energy half, mass is 10, the velocity is 12, that squared should be equal to, at the bottom it's going to be half. Okay, the mass at the bottom is still 10. Now the velocity at the bottom, we don't know that, so v squared. Actually we are finding the velocity at the bottom, not the work done by friction. We know that work done by friction, how do you find work? Work is friction times distance. But how do you find friction? Friction is given by coefficient of friction times the normal force, and the normal force, because it will be on a level ground, is given by mg, and then times the distance there. So mu k we've been given as 0.21. The mass is still 10, g is 9.8, the distance is 500. Alright, now we just punch on a calculator what we have. So we have got this 10 multiplied by 9.8 multiplied by 200 to give us 19,600, and then plus half multiplied by 10 multiplied by 12 squared, which is 720, and that will be equal to half into 10, which is 5 v squared, and then plus 0.21 multiplied by 10 multiplied by 9.8 multiplied by also 500, so that is 10 to 90. So if I take this over the other side, it's going to become negative, and it will subtract from this. So what I'm having is 19,600 plus 720, and then we're going to remove the 10 to 90. So that is going to give us 10,030. That will be equal to 5 v squared. So to remain with v squared, we're going to divide by 5, and that will give us 2006. So to remain with v, we square root that value. That is going to give us 44.8 meters per second. So that will be the answer then. Alright, last question in this one. We've been given a 2 kg block which is pushed up a rough 30-degree incline by 20 newtons force for a distance of 5 meters, as we can see. So given that the coefficient of kinetic friction is 0.5, we want to calculate the work done by the 20 newtons force, the kinetic friction, and also the force of gravity and the normal force. So let's start with the work done by the force, the 20 newtons force. Notice that the 20 newtons force is going in the same direction as the displacement. So the work done by that force is simply force times distance. We know that cos theta, the angle is going to be 0 because they're going in the same direction. So the force is 20. The distance is 5 meters. And then times cos 0 degrees. Cos 0 degrees is 1. So that will give us just 20 times 5, which is 100. Okay. So that will be 100 joules. Now the second one, we want to calculate. So we calculated the work done by the 20 newtons force. What of the work done by the friction? So work done by the friction is simply the friction times distance cos theta. Now notice that the friction goes in the opposite direction, because friction is going to be acting in this direction. But how do you find friction? Friction is given by coefficient of friction. So we're saying friction is given by coefficient of friction times the normal force. So just this portion here is giving us this. But how do we find normal force in this case? So the normal force on an incline, you have got a normal force there, you have got a weight force here. So if we extend the normal force like that, we can even join this. So this portion which is here is going to be equal to the normal force. So let's call this as y, because this is going to be the weight of the mass. So the y component of the mass should be equal to the normal force, and the y component of the mass is given by y is equal to mg cos theta, and this should be equal to the normal force because they are all in the y. Normal force is up, the y component is down, so they should be able to cancel out. So what we are saying is this is going to be equal to mu k mg cos theta. So that this will be the friction, and then we'll just go on substitute where it is. So I was saying work done by friction is simply friction times distance cos theta, but where there is friction is mu k mg cos theta and then times the distance. Now this cos theta which we are seeing here is not the same as this one which is here. Let me actually even use alpha here so that we just differentiate them. Alpha. This alpha is representing the angle of the incline. So that would be mu k, which is been given as 0.5. The mass is 2. Gravity is 9.8. And then cos alpha, the angle of the incline is 30 degrees. Okay, in that manner. So we've substituted mu k, we've substituted the mass, we've substituted g, and then cos. What of the distance? The distance we've been told it slides. Where is the distance given? A distance of 5 meters as given there. So a distance is 5. And then cos. So this theta is telling us the angle between the angle of the direction of the friction. Friction is going down. And then this thing is sliding up. So that theta is telling us this angle, which is 180. So if we punch this on the calculator, 0.5 multiplied by 2 multiplied by 9.8 multiplied by cos 30, then multiplied by 5, and then multiplied by cos 180. So that is negative 42.4. This is work. Work is in joules, so it will be negative 42.4 joules. So work done by friction is negative. That's why we can see that negative one. Okay, we found the work done by friction. What is the work done by gravity? So the work done by gravity mg. So we said mg is the weight force, mg, like that. So we want the component which is in the same direction, the component of this mass, which is in the same direction as the force. Let me just clean up so that we see clearly. Okay, so I've got a mass like that, and then we know that this mass has got a weight force. That is mg. Now what is the work done by mg? So if you recall, work should always be in the same direction as the direction of the displacement. So the displacement is like that. That is the 5 meters we can see. So it travels for 5 meters up. So the component of the weight, if we extend, we have of course the normal force here. So if we extend the normal force like that, and then we join now the extension of the normal force to mg, this will be the x component of this mg. So it is the x component, the one which is parallel to our displacement, which we use. So then the work done by mg is going to be equal to the x component of mg. So in that case, it will be the x component of mg, and then times the distance covered. So its x component is simply representing this one which is here, times the distance, and then cosine the angle theta. Now how do we find the x component of mg? Notice that the x component of mg is opposite to the angle theta there. So that is the mg sine theta. So that's how we find the x component, and then multiplied by the distance, and then cos theta. Again, I've used theta. This theta is representing the angle which is between the x component. Now notice that the x component of mg will be going down. That is because our mg is going in this way. So the x component is going to be going down. There's no way that the x component can be going on top if mg is going down. And then we know that the displacement is, this thing is moving up. So the angle theta is 180. So this theta is going to be 180. So that will be equal to, the mass is 2, g is 9.8, and then sine the angle, this is the angle of the incline, which is 30 degrees. And then the distance is still 5, and then cos 180. So 2 multiplied by 9.8 multiplied by sine 30 multiplied by cos 180. So what I'm finding is negative 9.8. Let me just replace again on the calculator. I just reconfirm. So we are saying 2 multiplied by 9.8, then multiplied by sin 30, then multiplied by 5, multiplied by cos 180. Okay, so it is actually negative 49 joules. So the negative sign means the weight is taking this thing in the opposite direction to the direction of motion. And then the last thing is the work done by the normal force. Okay, let's consider this. Been given in that manner, the normal force goes up, and then the direction of motion is like that. This is where the displacement is, and that's where the normal force is. So it was supposed to be work done by the normal force to be equal to the normal force itself times the displacement, and then cosine theta. But just cos theta, the angle here is 90, so that will be cos 90, and cos 90 is 0. So work done by the normal force is always 0. Alright, so that marks the end of this video. Thank you so much for watching. Stay blessed.